Funding for this program was provided by the Annenberg CPB project.
Oscillations can travel through a medium such as air or water without carrying matter along with them. These mechanical disturbances are called waves.
In any era, there are certain experiments which are just barely possible. These are experiments at the state of the art. They're a test of the skill and ingenuity of the very finest experimental physicists. An example today might be the attempt to detect gravity waves coming from distant stars. At the end of the 17th century, a state-of-the-art experiment was to measure the speed of sound. Sound normally comes to us through the air. If there were no air in this room, you wouldn't be able to hear me speaking. Of course, if there were no air in this room, you would have more serious problems, but that's another story. Sound travels very fast, but its speed is not infinite. We can tell that it takes some time because we can hear echoes, for example, sound reflecting from distant walls. And also, we can see lightning before we hear thunder because light travels much faster than sound. 300 years ago, one of those who tried to measure the speed of sound was Isaac Newton himself. His measurement was not the very best in his own era. Experimental physics is a special art, and it was not Newton's strong point. But of course, he was very clever, and it's interesting to see how he tried to make the measurement. At Trinity College, where he lived and worked, there was a long corridor that was known to have an echo. And he tried to measure the amount of time that it took for sound to get down the corridor and return. As a timing device, he used a simple pendulum. Now, you remember that the time it takes for a pendulum to make one full swing depends on its length. He arranged for a short noise to go off at just the moment that the pendulum was released. If the pendulum returned before the sound, it was too fast and had to be made longer. If the sound returned first, the pendulum was too slow and had to be made shorter. And in that way, he could get closer and closer to the exact amount of time that it took the sound to go down the corridor and come back, and thereby measure the speed of sound. Today, I would like to give you an intuitive understanding of what sound is. Sound is a wave, a disturbance that travels at a definite speed, like the waves in this machine. And a good point to start our discussion of waves is with two harmonic oscillators like these, which are coupled together.
Water, light, sound, even pressure. They all travel in waves. In fact, throughout the physical world, waves are one of the most common natural phenomena. And nature isn't the only one who can make waves. People can make waves of their own. And they've been doing it for a very long time. New York City, 1926. A big welcome for Gertrude Ederle, the first woman to swim the English Channel. But there's more going on here than meets the eye, much less the guest of honor. This is a human shock wave, with a circular wave front like the molecular motions of a sound wave in a gas. Notice how the wave moves from one person to the next, leaving a partial vacuum in its wake. This non-recurrent wave front was harmless. This one was not. Kennewitok, 1952. The first hydrogen bomb test. The world at large feels the heat of the first nuclear shock wave in the Cold War. But the phenomenon of spreading waves goes back considerably farther than 1952. Much farther back than 1926. It goes back to the very beginning of time, and the universe itself, in fact. The Big Bang. And from the very beginning of it all, a disturbance in one place, natural or otherwise, inevitably causes a reaction in another. And so it goes. Disturbed weather in a polar region causes trouble in the paradise of a tropical isle halfway around the globe. The chain of earthly events and phenomena, which are hooked together by infinitely complex links, is often better seen at a distance. But it can be better understood close up. That's because no matter how complex the system appears, an underlying principle begins to explain its physical aspects. When simple mechanical systems are joined, a disturbance in one will pass on to the next. When any stable mechanical system is disturbed, nature's response is simple harmonic motion. For a single oscillator, that's as far as it goes. But when oscillators are linked, from one to the next and to the next, a disturbance in one passes on to the next and continues on down the line. This is the essence of a mechanical wave. Sometimes individual mechanical oscillators are easy to discern.